Hello, everyone. Um, Welcome to the Stormwater 360 webinar series for 2024, or another installment of it. We'll just give everyone a few minutes for latecomers, and then we'll kick off with a bit of an intro and get into it. Just to make sure everyone's there. All right, well, we might kick off then. Well, welcome everyone. This is, I think, the third webinar for 2024, and I've been really looking forward to this one, as I'm really excited about the opportunity advanced green infrastructure solutions like Filterra offer to the world's environmental challenges, not only stormwater, but also climate change. Today's webinar is titled Filterra Performance Over Time. And Filterra is the world's first high rate, or as I like to say, high performance biofiltration system. It was developed over 23 years ago in the USA. And over this time, the Filterra has been monitored in diverse conditions in numerous countries by universities and research institutions to gain regulatory approval across the world, in Canada, New Zealand, Australia, also in Europe and Italy as well. Today, I have two speakers from our partners, Contech Engineered Solutions of the USA, Mindy Hills and Vaco Allen. Now, Mindy and Vaco were involved in the original development of Filterra and its continued monitoring and improvement and development of the solution to meet various regulatory requirements around the planet. Now, Mindy is a R&D project engineer with Contech Engineered Solutions. She has over 20 years stormwater industry experience. Mindy is responsible for product development and evaluation, as well as media quality control for stormwater treatment at Contech. Now, Vaco is the Director of Stormwater Regulatory Management at Contech, and Vaco brings over 2 decades of expertise in stormwater management, leading various stormwater treatment systems development and monitoring initiatives. He has contributed to technical guidance on performance verification, green infrastructure, and low impact development implementation, as well as TMD compliance and industrial stormwater regulations. Welcome, guys. It's really great to have you along. I've known these guys for nearly as long as I've been doing stormwater, so really good to have you along. Before I kick off, I would just like to briefly introduce Filterra, and in particular Filterra in New Zealand. The usual housekeeping rules apply, so you're all muted, but please chuck your questions in the chat, and at the end we'll come back and give you the opportunity to present them to the speakers. Will also be a recording of this webinar published on our website in the next upcoming days.
Mike, I think you're muted here.
Did you not hear my previous talk, or did I just mute when I flicked the screen?
Yeah, just when you flip the screen, so we're good.
Okay, thank you. Thanks, Vaco. As I said, yes, Filterra is the world's first high-performance biofiltration system, developed and invented in 2001. And it uses all the same treatment mechanisms as a conventional rain garden or a traditional biofiltration system. However, it's been designed and is implemented to achieve higher performance, more consistent performance, and also a much higher infiltration rate, allowing it to treat larger areas with a smaller footprint over time. Now, it was first installed in New Zealand in 2016. Stormwater 360 got a Callaghan Innovation Grant, and we spent 2 years developing the media and the system in New Zealand, because unfortunately you can't bring dirt and soil into New Zealand. So we had to work very closely with Contech to develop a New Zealand version of the Filterra, which is working, as well, if not better, than the US version, but we'll see. So the Filterra has private and public regulatory approvals right across New Zealand, so it can be used on public sites as well as on private sites in certain jurisdictions. And to date, we've installed over 578 individual Filterra units. That's the boxed concrete system that was a plug-and-play system that is delivered, as well as 8 Bioscape installations. And our Bioscape installer is a larger version of Filterra that is more constructed on site. So with the continued R&D via Contech and Stormwater 360, we've seen some great improvements over time. And today we're going to run through some of the performance data as well as the improvements. So on that note, I'd really like to hand it over to Vaco and Mindy to present.
There we go. Thanks, Mike. I think you're hearing me and hopefully seeing me as well. Great. All right. All systems go. Thanks for that introduction. I look forward to spending the next better part of an hour with you and talking through some insights from the world of bioretention and biofiltration. Just to kind of get on the same page at the beginning here, I just want to kind of talk a little bit about the history, and Mike already addressed this a little bit, but we've been doing this collectively for about 30 years, maybe a little bit longer than that. Some of the very first references came from Prince George's County in Maryland. And in particular, there's a 1993 design manual for the use of bioretention and stormwater management. That was kind of the foundational document. It's interesting to see how this system has kind of evolved over time. Initially, it was kind of like we think about rain gardens or just kind of depressional storage areas that mainly make use of the permeability of native soils. And at some point, they realized that they weren't draining down very quickly, and you might need to put an underdrain in if your soils weren't perking at an appreciable rate. So, the earliest kind of components of bioretention were described pretty well and haven't actually changed that much since the early to mid 90s. And of course, back in about, I think it was 1999, the Prince George's County released their low impact development manual, and that started to slowly take the world by storm, I guess you could say. So the specifications change or are different depending on your geography and your permit and other local requirements, but they're fairly similar, at least as I look around. In particular, on the west coast of the U.S., where I do most of my work, we have a 5-inch per hour standard design that's typically sand and compost, about 60 or 70% sand and the balance being compost. And that works out based on our local design storms to producing systems that are around 4% of the contributing drainage area. So these are conventional systems. Anybody can build them, and that's kind of one of the nice things about them is that they are usually available or can be built using local materials. Looking a little bit further from my home, but maybe closer to yours, Oh, actually, I have my slides out of order here. Before we get to that, let's just talk about bioretention and biofiltration just as terms. First thing I want to say is that terminology varies by region and permit, as it says down there in the bottom. Different people use different words to talk about the same thing, and it really is important to kind of make sure that we're talking about the same things. So as I usually think of it, bioretention is like an infiltration stormwater control measure, or SCM. Typically what we're most focused on there is sizing these things to infiltrate the water into the ground, taking advantage of the native soil permeability. And when we think about the effluent of these systems, what's really most important is protecting groundwater quality. In other words, we don't want to have pollutants go through these systems that could be a potential contaminator for groundwater quality. The other thing is that we want to protect the native soil infiltration capacity because we don't want them to clog over time, and then you've just got a failed bioretention system. So biofiltration is a term that is most often used where I do work to talk about systems that have an underdrain. So these are systems that are in most ways designed really identically to biofiltration, except that they have an underdrain in them. And that underdrain discharges all or a portion of the design storm offsite. So when you think about these systems, the fundamental difference is that when we're talking about effluent water quality with biofiltration, we're really most interested in what the effluent quality is for the purposes of protecting or restoring downstream receiving waters. So those are really different puzzles that we're trying to crack with either. And Filterra really fits more in the biofiltration category, at least with that nomenclature. So here's that kind of summary slide to look at how a lot of these systems are constructed in terms of the components that are that comprise them. And I pulled a reference here from the Auckland Council here, which even though it's a little more than 10 years old, it's still pretty up to date because these things don't change very fast in the conventional biofilter world. Typically, we're seeing mostly sand, some references to loam or loamy sand, or topsoil or compost for the organics, but typically pretty low infiltration rates, at least compared to what we're used to for proprietary systems or innovative systems. And this is kind of shareware, like people pass these recipes around and you see them appearing and getting copied from manual to manual often. So high rate biofiltration versus bioretention or conventional biofiltration, they're pretty different in some important ways. They both have similar unit processes and similar components, but the big difference is that the high rate biofiltration systems like Filterra, they have hydraulic loading rates, meaning the amount of water that you can infiltrate per time per area is much, much higher. So as an example, we have two projects here. We have the Whispering Firs project in the bottom, which is a Filterra Bioscape installation. That treats about 115 acres and has about 8,000 square feet of Filterra systems. Not just the one you're looking at here, but you can see some off to the side and the right. So pretty big installation, treating again 115 acres. In the top, you have a conventional biofiltration project, which also has about 8,000 square feet of conventional biofiltration, but the drainage area here is around between 10 and 11 acres. So you see an order of magnitude difference for the amount of flow that can be treated through the high rate biofilters. So aside from the first bullet here, the high flow rate resulting in much smaller footprints, the pollutant removal is really what I want to talk about most today. And that comes as a function of really two important things. One is just the quality control and the stability and rigorous kind of vetting of the materials that we use to make the Filterra media. The other is an important piece that sometimes is overlooked, which is around operation and maintenance. When you think about a smaller system like a Filterra, it is feasible to go in, and it's actually part of the maintenance requirements, that you go in and you maintain the mulch at a regular interval, sometimes 6 months or a year. And of course, when you remove the mulch and replace it, you're also removing all the pollutants that are captured in the mulch, where there are definitely going to be the trash and large debris, but also most of the sediment, and with that, a lot of the nutrient and metal loads. And then you replace the mulch and you're good to go till the next maintenance. Most conventional systems, they just, maybe rake the mulch here and there or top it off as necessary, but it's typically not required or even suggested to go and replace the entire mulch bed. So that, in addition to the kind of consistent design that we have as a modular system, really is where a lot of the benefits from a pollutant removal perspective come in. So speaking of pollutant removal, there's a couple of verification programs out there, and I want to talk about the Washington Department of Ecology program, because even though it's administered by the Washington Department of Ecology, the TAPE program, it is recognized really around the world as the preeminent field monitoring program, or field performance verification program. It includes an independent advisory team that actually reviews any data that's submitted to the program, and it's like a peer review process. People are PhDs and people who are kind of represent the pinnacle of stormwater BMP understanding, in terms of how they work and how they perform. They will review all the data that are submitted, and if you pass their criteria, you can get a general use level designation. You need to measure at least 15 storms and meet a bunch of other criteria too, but at this point it is the best thing that we have for demonstrating performance of biofilters, or really any stormwater control system in the field. So the TAPE program has set a few goals. It's important for biofilter purposes really to focus on the first three: basic treatment, dissolved metals treatment, and phosphorus treatment. And they've done a kind of interesting thing here. They've constrained the influent characteristics, for the sites and for the storms that you can submit to the program, to make sure that we don't have really unusual, for example, unusually high influent concentrations of sediment, or or unusually high metals concentrations, which can be easier to show high removal of. So by constraining the influent concentrations, it makes sure that all the data that goes through the program is somewhat comparable. They also require that the particle size distribution for your incoming stormwater solids is pretty similar. It should be in the silt loam range, or in other words, predominantly in that silt size fraction or finer. So with those kinds of safeguards and standardizations, the data that comes out of TAPE is very interesting and useful in comparing technologies one to another. And not just comparing the technologies that have been through it, but also to, as we'll do in a minute, comparing the performance of technologies that have been through the TAPE program to conventional systems that maybe haven't. So the TAPE program has been around for a long time. I don't exactly know how long. It's about 20 years, as my recollection. And it's changed a bit, but there have been a lot of biofilters to go through, and I've listed them all here. You can see that the thing that I really wanted to note here is that there are proprietary and non-proprietary versions. For example, the city of Bellingham has their the phosphorus optimized stormwater treatment system that's been through the program and got basic and phosphorus approval. So we're not just talking about proprietary systems here. Really, any system can go through. So we often are asked, at least I'm often asked in my regulatory role here, how do you know if your systems, meaning Filterra really, are working as well, or maybe better or worse, or how do they compare to conventional systems? So of course, to answer that question, we have to know a couple of things. We need to know how well the Filterra system works, which we've been collecting a lot of data on, and we know pretty well how that works. But we also need to know how conventional systems work. And it turns out that that's a little bit of a harder puzzle to crack. So back in about 2014 and 2015, I worked with Geosyntec to create a report that's available online that is called the Filterra Equivalency Analysis and Design Criteria report, and that was prepared for the Los Angeles Regional Water Quality Control Board. In that study, we looked at conventional biofiltration system performance and Filterra performance and compared the two. More recently, I was doing some work with San Francisco and San Diego water boards, and they asked really similar questions. So we went back into that data set that we had created in the 2015 report, and we decided to refresh it and update it. So we took the most recent version of the International BMP database, which came out in 2020, the summary report. We took all the studies from that report that had that reported on biofiltration performance, 79 of them, in fact. And we added a few studies that, for whatever reason, weren't in the BMP database, but that were of reporting on systems that were very similar in composition and to the conventional systems, and sized similarly. And then from that 79 bioretention studies, we got rid of some of them. We got rid of the ones that either had called out things like issues during construction or premature clogging, or that were high-rate systems. There were a couple Filterra systems in there, so we took those out because we didn't want to compare Filterra to Filterra in that way. We also took out ones that had internal water storage because that was specifically designed for nitrogen that we're not required to do in California. But at any rate, we ended up with a really robust data set for conventional systems, and we can compare that to Filterra. So what I'm going to do in the next few slides here, if you'll indulge me, I think this is kind of fun to look at data in this way, is to show these kinds of plots for different pollutants with Filterra on one side and conventional bioretention on the other side. So the way that these plots work is that the line that is in blue is the line of no change. So if you're on that line, you don't have any difference from influent to effluent. If you're below it, then it's a removal event. If you're above it, it's an export event. And all the little turquoise, aqua triangles, those are all individual storm pairs, so influent and effluent pairs. And it's a little bit hard to see on this graph here because the data is so tight at the bottom, but there is a median value that you can see in the little boxes there, and then a 95% confidence interval around that median. This could be a whole presentation in itself, how these work and are calculated, but I'll spare you the details here and just flash these up in fairly quick progression here so that we can kind of get a quick visual to see how well these systems can compare. So the first thing we notice, right, is if you look at where all those blue dots are for the Filterra sites, they're all pretty much all below the line, meaning that we have removal consistently. A little bit different, especially at very low influent concentrations with conventional bioretention. So we know that the media sometimes itself can be lost out the outlet pipe. But generally, both systems are very good. When the influent concentration is really anywhere between 0 and 600, it's going to come out pretty clean. So both systems are very good performers for solids. Looking at total copper, the story gets a little more interesting. You see a lot more scatter in the conventional systems. And a lot more export events, especially at the beginning, as compared to Filterra. And both systems do pretty well for copper removal. Next one is total zinc. So again, we see a kind of similar story, a little bit more data scatter in the zinc plot, but both systems are pretty good. Actually, the Filterra system maybe doesn't perform quite as well at the very high influent concentrations. I think part of the reason for that is that most of the test data that we have for zinc is coming from sites where we are trying to find high fractions of dissolved zinc. In particular, we have a couple of studies now that have been done at our Hillsborough plant for Contech, where we literally manufacture corrugated metal pipe, which is often galvanized. So there's a lot of zinc and a lot of copper moving around on site. We tested those sites specifically because they have a lot of dissolved copper, and we can get up into those ranges of interest by the Washington tape program. So that might kind of skew the Filterra results here, but in general, both are pretty good for zinc as well. Gets a little more interesting when we talk about nutrients. So looking at nitrogen here, you see that those confidence intervals, I don't know if you can see my cursor here, but they're actually above the blue line for a big part of the range here, meaning that there isn't necessarily a significant reduction in nitrogen that's happening with conventional bioretention. And there is a more consistent export at very low influent concentrations. So just not very good for nitrogen. As compared to that, Filterra does a bit better. And it gets really ugly when you look at phosphorus. Most of the stormwater is coming in at less than 0.5 milligrams per liter. And if you're substantially below that, then you're actually more likely to be exporting phosphorus than you are to be removing it with a conventional system, really due to the compost content. Now, if we look at the Filterra system by comparison, much more consistent performance and much better performance. So I hope you enjoyed looking at these plots, and I could go on and on about that, but I'll spare you that, and just kind of go to a couple of summary slides here for performance. So we take the information that we looked at just previous to now, and we line it up with what we expect typical concentrations to be for, say, a commercial land use. This is, again, for California influent, but I imagine it's not too dissimilar where you are. At a median influent quality of TSS for about 53, you can see that high-rate biofilters, Filterra specifically, gets about a 91% reduction. Conventional bioretention gets about a 77%. So for TSS and nutrients, really conventional biofiltration, it isn't so hot, especially for nutrients. Much better performance with Filterra, and pretty similar performance here for metals. Remember, we talked about the zinc kind of reasons why those might be different. So if you stand back and squint, you can say for sure, Filterra provides at least as good, or if not better, removal for sediment and nutrients, and probably comparable for metals. There's another way to look at this data that comes from the BMP database. So this is just the data that's in the BMP database with no extra studies, no screening or anything. We can compare that data for conventional biofilters to the tape criteria, which of course we meet with Filterra and other biofilters as well. We see that, again, conventional biofilters good for sediment, not so good for nutrients, and they do not meet for dissolved zinc or copper, which the Filterra system does. So now we're kind of drilling into that dissolved copper and dissolved zinc criteria that tape has. So would they meet the tape standard? Yes, for TSS or basic treatment. Definitely not for phosphorus, and no for dissolved copper and zinc. So we think so far we've got a pretty good story here, in terms of comparative performance for Filterra versus conventional biofilters. Let's add another wrinkle, though, which is load reduction and volume reduction. This, again, is a slide that could be a whole presentation, but I will just give you the quick cliff notes. When we think about how well a system does from a pollutant removal perspective, we have to really think of 3 different things. How much water goes into the system, meaning how much is not bypassed. We think about the concentration reduction, which is really all that we've been talking about so far. But there's another piece. There's the runoff reduction part, like how much of the runoff actually goes into the ground or is lost, by infiltration, or is lost to evapotranspiration. It turns out that if you kind of stack these criteria, these terms together, you see some differences. For capture efficiency, like how much water goes into the system, usually that's a regulatory requirement. So whether we're talking about conventional systems or tape-approved systems like Filterra, it's going to be the same. We know from all the data that we just looked at that Filterra is going to be a much better performer for most of the pollutants that we're interested in. But there actually is an advantage on the conventional biofiltration side that is about runoff reduction. So sometimes, especially if you have highly permeable soils, those systems can infiltrate a lot of water if that's allowed. So we asked a key question here, which is how much runoff reduction do you actually need to have by conventional biofiltration to overcome the concentration reduction advantage that you get from Filterra? And rather than go through the whole proof to get to the end of that other presentation, I'll just tell you, you need about somewhere between 0.3 and 0.5 inches per hour of native soil infiltration for these conventional biofilters to start to reach the level of performance that you would get from a Filterra with no infiltration whatsoever. So anytime you're in soils that are around 0.3 to 0.5 inches per hour or less, which is a lot of the soils we end up working with, Filterra, even without any infiltration at all, is still going to be providing a better pollutant load reduction. So that's important to me. I hope that was easy enough to understand, and if you want to ask questions about it later, we'll be here. So another piece of the puzzle that's important here is talking about longevity, and I'm going to shift it over to Mindy here in just a second. But before I do, I just want to note a couple of deficiencies or kind of gaps in our understanding that come from our reliance on tape as a verification program, and to some extent the New Jersey program as well. Looking at tape here, we're really pushing the hydraulic loading rate for these systems, basically trying to get more water to go through them while still being able to meet those performance goals. And I'm looking at the biofilters here, or in this table you have all the biofilters that have gone through the program recently. I don't have the hydraulic loading rates listed there, but they're getting higher and higher. And you can see the longevity information that's in the general use level designation. For Filterra, we were right there at our typical maintenance interval, which is suggested to clean the mulch out at about 6 months based on about 40 or between 35 and 40 inches of rain in the Pacific Northwest. So we were right on our standard maintenance. Some of the other systems, which I've grayed out so that to protect, I guess, them, they didn't do so well. At the bottom here, we have a system that just recently was adopted with 1.7% of the water year on average as the amount of flow that could be treated between maintenance events. That's basically a storm or two. The one that is in 2021 that went 83% of a water year between mulch replacement, that's actually the non-proprietary version that we talked about in Bellingham before. So you can see that we might have an issue. If we're just focused on performance, we're not necessarily looking at the long-term capabilities of the system. Like, are they even able to pass the flows that we're expecting? Sometimes people send me biofilter pictures. The one on the right here, a friend of mine was up in Portland, Oregon, and they said, "Hey, is this what your company does?" And I said, yes and no. Thankfully, that's not a Filterra system. That's a conventional biofilter, and the local residents had made a sign and put some floaties in there. That thing's not draining down. It's not raining, and it should be empty, but it's clearly not. So, these are things that can get missed in short-term monitoring. Pretty much all the data that we've looked at so far has been short-term monitoring. Systems that are either new or in at least pretty good condition and fairly new. And usually the monitoring, it happens over 10, 15, 20 storms, which might take a year or 2 years, usually not much longer than that. So we have some fundamental questions that are left over after we get through tape and whatever other performance verification programs. And some of those questions are here, like, does the water quality performance change? Does hydraulic capacity change? Will your vegetation survive? And in particular, for Filterra, where we have a higher hydraulic loading rate than conventional systems, and therefore a higher pollutant load per square foot, how does that impact things over time? I'm not going to tell you the answer, but I'm going to hand it over to Mindy, who can walk us through some research that we've done to really get directly to these questions. Thanks.
Is the transfer working? Mindy, you're muted if you didn't know.
Thanks, guys, and thank you, Vaco. Can you guys see my screen okay?
Looks good.
Perfect. So just to follow up with Vaco's kind of setting the stage here, one of the questions is, why do we think high-rate biofilters would demonstrate good long-term performance? And the biofiltration components and practices listed here really support the hydraulic and quality performance longevity. So it starts with the right recipe, which is design. And that's really more of the easy part. The biofiltration components, they support the biological treatment mechanisms, which are really just a synergistic community of living organisms. So that's the plants, that's the microorganisms, that's the organic media to sustain long-term quality and hydraulic performance. These components play a major role in regeneration of hydraulic function and pollutant removal capacity. The harder part is really the quality control, and that's just ensuring that each component and blended media meet the physical, chemical, and hydraulic specifications. QA/QC procedures are really critical to ensuring media consistency and function per the design specification. Installation and activation are common failure points in conventional systems. Filterra is a repeatable design, and just the procurement and activation processes really minimize the opportunity for contractor error. Equally important is routine maintenance. Replacing the mulch is essentially changing the media pre-filter. The routine maintenance is critical to quality and hydraulic design sustainability. And it's as simple as just removing the degraded mulch along with sediment, trash, debris, and replacing that with new mulch and doing some vegetative pruning. The maintenance, it's permanently removing the contaminants from the system. And organic mulch replacement also replenishes organic content in the media and it supports those treatment processes. So to understand high-rate biofiltration long-term performance, 3 Filterra sites were selected in the Mid-Atlantic region of the US. This is in Virginia and Maryland. The sites represented 3 different land uses, including a restaurant commercial parking lot, which is study site A, an oil service station, site B, and a gas retail area, site C. Sites also represented different system sizes, plant types, and system ages up to 13 years old, and monitoring duration ranged from 3 to 11 years. We contracted with third-party labs and quarterly grab samples were collected. The local labs we used were Universal Labs and Microvac Labs. They followed EPA sampling guidelines. So they collected every 30-minute duration at 10-minute intervals. We were trying to target the first flush. Storm event criteria included antecedent moisture conditions of at least 6 hours and greater than 0.1 inches of total rainfall depth. Water quality analytical EPA or standard methods were conducted following proper handling requirements for TSS, various forms of phosphorus and nitrogen, total metals, oil and grease, TPH, pH, and temperature. After over a decade of quality monitoring, as a final step, we really wanted to correlate flow and quality performance. We selected study site A for the hydraulic evaluation, which was 14 years old at the time of hydraulic testing. Hydraulic evaluation was not performed at the other 2 study sites, so that was study site B. They had an oil spill in 2011, and that resulted in just full remediation of the Filterra system media. So replacing that media with new media basically rendered any future flow data irrelevant when compared with the pollutant removal testing. And Site C was decommissioned in 2018 for site reconstruction and fenced off, preventing any additional testing or maintenance. So Site A was really the only site remaining at the time for hydraulic evaluation. Hydraulic field evaluation was based on a prior protocol developed in consultation with geosyntech consultants for the Filterra system, where we monitored rising, constant, and falling head. Testing was performed in 2 phases. We had an unsaturated phase that was followed by a saturation phase. The first test allowed for observation of the system flow rate under more typical dry conditions with less available water content, where we have preferential flow paths, we have moisture deficit, that can all influence flow rate. The system's brought to bypass, the media is saturated, that's followed by a drain down period to bring to field capacity and provide a more uniform moisture test condition. The second test following that same procedure allowed for observation of flow rate under like a more worst case atypical saturated condition. So that's producing a more conservative measurement of flow through the media after being fully saturated, whereby antecedent moisture conditions are more uniform. The source water was from the hydrant, so that was controlled manually and directed to a flow meter via a combination of a flexible fire hose. We had some PVC piping. We measured by a factory and field calibrated electromagnetic flow meter that was logged at minimum intervals of 1 minute. The logged flow was used to verify testing was conducted at the target flow rates. Influent water was conveyed to a factory and field calibrated rotometer for secondary flow verification before discharging into the gutter, just to mimic more real world runoff. The flow rate was held steady during the test, about plus or minus 10% of the target value, and a ruler was secured to the inside of the Filterra system to monitor fluctuations in the water surface level and the headspace of the unit. So I'll be sharing TSS, select nutrients and metals data, but additional pollutant species can be found in our study report, which is linked at the end of this presentation. Baco's kind of already discussed the TAPE, the Washington Department of Technology acceptance protocol. We used their influent criteria and applied that to TSS in this evaluation. So we excluded concentrations that were below 20 milligrams per liter in the influent, which is fairly standard practice. So we're not evaluating clean stormwater. The regression intervals are different than the bootstrap confidence intervals that are used in the TAPE program, where influent concentrations are capped and the data is resampled many times. The regression scatter plots were done just to understand TSS effluent concentration performance over time. We have years on our x-axis, effluent concentration in milligrams per liter on the y-axis. The confidence interval line indicates there's a 95% probability that the true linear regression line, so that's our best fit line of the population, will lie within the confidence interval of the regression line that's calculated from the sample data. The prediction interval, that's indicating there's a 95% probability that future concentrations corresponding to time will also fall within that interval. The R-squared value here is indicating there is no correlation with effluent concentration and time, and the majority of the effluent concentration is falling below the 10 milligram per liter concentration. Looking at the linear plots here, we can see that or box and whisker, sorry, for TSS, we're looking at, on the right side, we've got common sort of visual descriptive stat tools that accompany this table on the left. So the plots are showing the TSS influent and effluent concentration confidence intervals. As indicated by the notches that you can see on the box, you can see that these don't overlap. So we're demonstrating statistically significant differences between influent and effluent concentrations with a tight effluent concentration distribution, again, under that 10 milligram per liter concentration. Due to time constraints, I won't cover the entire summary tables here, but median influent removal efficiency were 48, 5, and 90% respectively. We used a Mann-Whitney rank sum test to show statistically significant differences between influent and effluent, and you can see we are seeing that difference with a p-value of less than 0.001. Correlations further supported by line plot analysis showing influent and effluent concentration over time. And this just provides a visual difference of performance over time at each site. We can see variation in influent concentration with consistent effluent concentration. This analysis had to be done by site, since the influent and effluent are paired by site, and adding multiple sites really makes the figure illegible. Tape influent concentration criteria were applied to total phosphorus, excluding influent concentrations below 0.1 milligrams per liter. Again, very standard practice, so we're not evaluating that clean stormwater. The regression plots were done to understand, again, total phosphorus effluent concentration performance over time. And again, we see that R-squared value indicates there's no correlation with effluent concentration and time. The box and whisker plots show the total phosphorus influent effluent confidence intervals. Again, we see these notches are not overlapping. There is statistically significant difference. Abnormally high influent concentrations were observed at study site B. That's the oil service station where there was evidence of the bay actually being washed down. So we had washed down water entering our system, and likely that was influencing these outlier concentrations. The median influent effluent removal were 0.2, 0.09, and 60% respectively, with our stats test showing us a p-value of less than 0.001, showing statistical difference. Again, correlation with the line plot, we see that there's variation in influent concentration with consistent effluent concentration, even at study site B where abnormally high influent concentrations were observed. Again, with the regression scatter plots, this is for total Kaldol nitrogen. We see that the R-squared values indicate there's no correlation with effluent concentration and time. The box and whisker, again, for TKN, we see the notches are not overlapping, so we're seeing statistically significant differences. Our median influent and effluent removal were 1.4, 0.66, and 42% respectively, with p-values less than 0.001. Correlation, again, with line plot analysis, we see variation in influent concentration with consistent effluent concentration, with higher influent concentrations producing higher effluent concentrations. Again, with the regression scatter plots, the R-squared value for total zinc is showing no correlation with effluent concentration and time. The box and whisker, again, we don't have overlap, so we're seeing, when those notches, we're seeing statistically significant differences. Median influent effluent removal were 0.14, 0.5, and 63% respectively, with p-values less than 0.001. Again, with the line plot analysis, we see variation in influent concentration with consistently low effluent concentrations for zinc. And then we also looked at total copper. Again, the regression showing no correlation with effluent concentration and time. Box and whisker, again, no overlap in the notches. We have statistical significant difference. Removal or median influent effluent removal were 0.029, 0.01, and 57% respectively, with, again, p-values less than 0.001. And again, the correlation with the line plots, we're seeing consistently low effluent concentrations over time, given variation in influent concentrations. So now that we're past that, the Filterra's long-term performance was compared to the BMP database results, like Vic has already introduced you to, for high-rate biofiltration comprised of just Filterra field studies for that category, essentially allowing us to compare short-term to long-term performance. The values differ slightly from the TSS and P medians in the previous slide, where tape influent criteria were applied, and this is how the BMP database evaluates data. These are the only parameters with data from both sources. Removal efficiency was significant for all parameters, with TSS and phosphorus median influent and effluent values nearly identical. Total copper concentrations were greater, as was removal efficiency, and total zinc concentrations were lower and removal was similar. The nearly identical data sets from both sources indicate that Filterra long-term performance is similar to initial Filterra performance for these parameters. Separate analysis was completed for the initial unsaturated and saturation tests. Following that third-party consultation on recommended analysis procedures, hydraulic evaluation was conducted via 3 different analyses for, again, that rising constant and falling head. The Filterra media hydraulic evaluation demonstrated a dry, typical condition, median infiltration rate of 177 inches per hour. That's around 4,500 millimeters per hour. That's in line with Filterra's Washington Department of Ecology's general use level designation approval rate of 175 inches per hour, or around 4,445 millimeters per hour. The Filterra media wet or saturated atypical operating condition median infiltration rate was 107 inches per hour. That's equivalent to around 2,700 millimeters per hour. So given that all 3 systems were originally designed based on a media flow rate of 100 inches per hour, so that's around 2,500 millimeters per hour, The unsaturated rate of the 177 inches per hour really proves that the system continues to outperform expectations, even after 14 years by a factor greater than 50%. In fact, the saturated media flow rate, of 100 inches per hour, that 2,500 millimeters per hour, that meets the original design flow rate. This study further supports the prior flow rate field evaluation report, whereby we flow tested 15 different Filterra units of varying ages, up to 5 years, sizes, maintenance periods, up to 2 years without maintenance. And we demonstrated a minimum 95% confidence interval infiltration rate of 140 inches per hour, which is around 3,500 millimeters per hour, and a median of 164 inches per hour, a little over 4,000 millimeters per hour. So the 14-year study, it was just really nice to see this hydraulic data really align with the prior study. The media profile of the flow tested system was also evaluated to look at composition to understand system dynamics. Does the media that went into the ground 14 years ago at steady state A, does that still look the same? And just understand whether the media composition supports the quality and hydraulic performance observed over the monitoring life of the system. Results show the organic content analysis average varied by 0.44% over the same profile depths, but by only 0.03% when that first 3 inches is not included. The particle size analysis showed less than 3% difference in the average gravel, sand, silt, and clay percentages among all the media profile depths, so that was 3, 6, 9, and 12 inches. Increased organic content and silt and clay were observed in the media surface, placing media outside specification in the first 3 inches, but otherwise the media remained in spec after 14 years of operation. Plant growth progression was also evaluated over time at all study sites. So, did the plants that went in, 6 to 14 years ago across the sites grow? And we found plant height and width for all study sites increased 1.3 to 2.4 fold and 1.7 to 3.2 fold, respectively. We'll just conclude with answering some research questions and recommendations for improving biofilter longevity. One of our initial questions was, do plants survive and grow over time? Well, yes, we see that in the data. And plants, they're phytoremediators. They support microbial activity. The roots sustain hydraulic capacity. And there's research out there to support the creation and sustainment of preferential flow paths made by the vegetation that support higher infiltration rates over time. The plants and organics, they really facilitate a sustainable biological cycle just through regeneration of hydraulic function and pollutant removal capacity through decomposition, degradation, uptake of captured pollutants. The organic matter that's within the engineered soil media is sustained over time just to replenish absorption capacity through the influx of organic material into the stormwater runoff, the plant roof die-off, we have mulch degradation, and we have replacement of mulch at maintenance. The microbes support nutrient cycling through organic matter and compound decomposition and biodegrade pollutants into less toxic forms. So where applications allow for vegetative plantings, let's plant them and really keep that bio in biofilter. The other question was, does quality, performance, and hydraulic capacity change over time? Well, no, as evidenced in the data. But you must complete quality control and routine maintenance. This is critical. You should review initial batch certifications to ensure media aligns with the specifications and that the certification is current. You may also consider replacing the first few inches of media after 10 to 15 years. It was evidence that the media profile composition was similar to the original, but when the maintenance duration was exceeded a few times at the site, it's likely that did contribute to some increased fines in the surface layer in study site A. I've mentioned that mulch is important for media protection, organic replenishment, but you also have to think about how you're sourcing your mulch. And organic mulch, so not rubber, not stone, that really serves as a carbon food source for microbes. In the States, we look for certification on the mulch bags by the Mulch and Soil Council, which requires certain criteria. Double shredded mulch is recommended. If it's too large, it's going to float away. If it's triple shredded, it might impact permeability. The mulch serves as a sacrificial layer. It's pre-treatment. It's supporting the treatment processes within the media. And you can just see these photos, look at the preserved media and the white roots in the picture to the right after spent mulch was removed. Also, just replace, not just replenish the mulch so it doesn't turn into soil and reduce hydraulic capacity, which is sometimes done with conventional systems. And we will also want to just permanently remove those contaminants from the system. Many localities are including a regional management approach as part of their watershed compliance planning to maximize utilization of usable land, to reduce total capital costs, operation maintenance costs, to provide a retrofit potential for existing areas. And just there's the aesthetic and communal benefits as well that accompany regional systems. Equally important is that regional systems also assure systems are more likely to be maintained because they have very high visibility. However, there are design measures that should be considered if you're scaling up your biofilter. A sizing factor of safety allows for contingency in design. If the in situ treatment area differs or if maintenance frequency is exceeded, causing reduced drain down time or premature bypass. With larger systems, the time of concentration can increase significantly, so there should be consideration in the design just to ensure appropriate rest periods to allow that media to endure the wetting and drying cycles that help sustain hydraulic and quality performance. After installing or also just installing some sort of inflow distribution across the media filter surface area ensures even loading across the media bed versus just like the inlet side receiving increased loading as exhausting absorption sites more quickly and smaller events not making it to the other side of the bed. Lack of maintenance can result in biofilter premature bypass, delayed drain down times, pollutant export, thereby no longer meeting the stormwater quality and quantity criteria. Maintenance also allows, what I really like about it is it's diagnosing issues that maybe weren't obvious at installation of newer systems. So, standing water could suggest flow restriction or premature bypass. Evidence of excessive scouring could cause short circuiting of a system. That can be remedied maybe with some energy dissipation stones or flow splitters. Slopes can be assessed around the practice for proper vegetation establishment during maintenance visits. They can be replanted, regraded if necessary, if compaction or channelization is observed. And obviously, like dead plants may be an indication there's a more severe issue going on. They really serve as a visual health indicator. Maintenance should be really a forethought in the project planning and design phase and not an afterthought. So we're not enduring expensive restorative costs later on. Maintenance should also be accounted for in life cycle costs when comparing it to other treatment systems, just to really understand the full cost of the system over time so it can be properly funded and planned for. When considering different treatment practices, reviewing the maintenance frequency and % water year monitored in the field monitoring reports, as Veiko already touched on, is important. This will help make decisions on whether the maintenance will be burdensome and overlooked or manageable long-term. Having a maintenance specification in the locality permits also helps ensure maintenance longevity by enforcing it through a permit. Maintenance evaluation should also be part of any stormwater control measure verification or certification program to understand the maintenance requirements and frequency for the treatment system to properly plan for maintenance long-term. These are just some resources for different links for some of the reports we touched on. This presentation is recorded, so these will certainly be available later. But in those includes our link to the International BMP database with a lot of data that both Veiko and I have shown. We have the Filterra equivalency analysis and design criteria compared to conventional systems. There's a report on that. We also have the longevity study that I've just presented. We have a short report summary of that. And then for those that like to get in more of the science and the details, we have a longer term report on that as well. And with that, we'll take questions.
Thanks, Mindy and Veiko. Yeah, plenty of research and plenty of data and really impressive. All those reports are also available from Stormwater 360 that just Mindy mentioned there, but we'll kick off some questions, and I might start just before we get into these questions, really kind of for both of you. You were comparing the performance of Filterra with a traditional biofiltration system or a rain garden. Now, are there any regulators or municipalities accepting it as a equivalent solution to a traditional biofiltration system?
Yes, more and more. For a while we were in the kind of, as we call it sometimes, battling magic with science, which is always a losing proposition. But we got the science, and there's kind of an assumption of performance for conventional systems. But I think as people are testing them more, especially with the conventional blends using compost, they're really starting to understand for nutrients, especially the shortcomings there. So was actually just working on a project last week, a very large project where they're not allowed to put in conventional biofiltration because they have a TMDL downstream for nutrients, and they're specifically looking at Filterra media, because nitrogen and phosphorus are pollutants that they're worried about. So I would say it's now more the outlier where it's not allowed as conventional, where it used to be the other way around, 10 years ago or so.
That's really good to hear, because we're seeing some regulations in New Zealand too, where the standard is going to be a rain garden as the required level. So that's good to see it's being accepted as an equivalent performance. Well, maybe this one for you, Mindy. You talked a bit about, if maintenance was missed or things like that. And this also relates to Andrea's question that has concern about biofiltration in the Christchurch port area, because Port Hills area, because of the high sediment loading. What can you do if a system doesn't get maintained or gets really hammered by excessive sediment loading?
Yeah, and maintenance frequency oftentimes is just dictated by your land use. So if you're in an area where you do have heavier sediment loading, you might want to reconsider maintenance frequency. Maybe you do need to maintain that system a little more often, but I think also being out there and inspecting it during a storm event to see, is it maybe a more intense event, to see if it's meeting design flows. You obviously can also consider in situ testing and, go out in there and maintain it. And maybe if it's been sitting there with overloads of sediment for a long period of time, you might need to consider taking off the first few inches of media. The mulch does an amazing job as pre-treatment and protecting the media. And so if that is removed and replaced maybe with the first few inches on a heavy loaded site, that would probably remediate the issue, but you would often or eventually just need to go out there and probably test it or see it during an event to confirm.
Yeah, that's
something that we do here in the States too, is like if we're not sure or if there's some sort of visible issue, maybe standing water or what have you, we'll take samples of the media profile and actually look at whether or not the media integrity has been impacted, or if it's just at the surface, and can say, hey, you only need to go down to 6 inches and then you'll be fine.
Yeah, we've been actually monitoring the very first one Biofilterra we installed in the Auckland Botanical Gardens for nearly 8 years now. And at one point in time, we did have a kind of like a truck dump a whole bunch of topsoil into the Filterra, and we removed the top 200 mils of sediment of media, as well as the mulch, and the system is still performing at pretty much design flow rate, 8 years later as well. So, yeah, I think you can get in there and remove that. And we did exactly as you said. We took a sample and looked for the PSD, and it was lots of fines in that top 100, but we took 200 out. I will just go through some of these questions, and some of them have got New Zealand context, which I'll jump in as well. How long, this is from Mohammed at Auckland Transport. Good to see you're on the webinar, Mohammed. How long will this device perform to its full capacity without compromising water quality requirement? I guess that alludes to saturation. Will the device eventually get saturated or full of contaminants and the performance drop? Either of you?
The media, yeah. The media is really designed to, last indefinitely. It's really the mulch replacement that's critical. If you're not maintaining it, over time, you're leaving the contaminants in the system, right? They're going to eventually leach out and saturate that media. So we want to ensure maintenance. And, it might be somewhat dictated upon what constituents that you're after. If you're in a site that it's loaded with fertilizer all the time and it's just saturated with, soluble or, phosphorus, then that might be something that, you want to consider, well, maybe I need to vegetate this a little more heavily. Maybe I need to do some monitoring to see, what does that look like, long term?
So if you had an unusual site, there's adjustments that can be made, essentially, whether it's maintenance frequency or vegetation or things like that. Mohammed had a couple of other questions here about, do we have any performance monitoring in New Zealand conditions? Yes, we do, and this actually would help you, Vaco. I shared it with Contech before, but maybe you didn't get it. But we did a study over couple of years ago with Christchurch University, looking at the performance of Filterra for treating galvanized roofs, and we had very high influent concentrations up to 10,000 micrograms per litre, and we were achieved 99% of dissolved metal removal, but there was only zinc coming off the roofs. There were no other contaminants. So that, that is something you need to consider, the contaminant mix. We also have quite a lot of industrial permit data with grab samples, a bit like the performance over time, because we've been using Filterra as a polisher in industrial applications. And just Mohammed also asked about the infiltration rate compared to GDO1 Auckland Council regulations, and yeah, so the Filterra, we typically used to design it at 100 inches an hour, as Mindy said, about 2,500 millimeters. Now with their new approval and a new design, it's up to over 8,000 millimeters an hour, and that compares to about 300 millimeters an hour with GDO1. So it is a magnitude of 10 to 20 times higher flow rates. Abby Sharma from Auckland Transport has also got a question. I got a good question here. With climate change occurrences, more storm events, more intense and more frequent, how can Filterra kind of be designed to manage these? And is there any risk with climate change?
Yeah, but there's a couple of different ways to think about it, and I'll just pick one. There's a lot of retrofit work happening as a, just to make sure that we're not degrading our downstream waters, but also just to deal with surges of flow and high flow rates. One thing about having a compact system like Filterra is that you can squeeze it into small spots where you wouldn't necessarily be able to put conventional systems in. So we are seeing a lot of retrofit work that is really in those space constrained situations. So that's a little bit of a twist on the question. It's retrofitting for the purpose of anticipated higher flow rates and more pollutants coming off potentially. I guess another way to think about it is that the Filterra capacity is typically higher than what we're designing it for. So if we're designing, it'll have additional capacity. There is no flow control within the Filterra, outside of the media, either upstream or downstream. So if you have a 20% increase in flow, you're probably still going to be able to treat that flow. Like, it's not necessarily going to bypass the Filterra system as long as you stay on the operation and maintenance of that system. So there is, in a way, a little built-in capacity. That's different than a lot of other biofilters, which actually have an orifice control in the outlet pipe, for example, or some kind of a control somewhere else that limits the amount of flow through the system.
Mm-hmm. And one thing that they are advocating green infrastructure for is the retention capacities. Can you design a Filterra with retention as well?
For sure. Lots of different ways to do that. The simplest version is like we see in some of the Bioscape versions, where you're just installing the system in contact with the native soil. So in other words, not in a concrete vault or not within a liner. So you get some infiltration there, but if that's not enough, absolutely there are things you can do, either adding additional infiltration capacity downstream in the form of chambers or perforated pipe, or just a kind of a soak away, gravel trench kind of thing. So lots of options. And even if it's in a vault, we have designs where you basically can just perforate the bottom of the vault itself and maybe put that on a larger, gravel footing or gravel bed that extends either deeper than typical or wider, outside the perimeter of the vault itself. So lots of ways to do it. Limited by your imagination and site constraints.
We've been doing a bit of monitoring of volumes in and volumes out of a box system, and also finding a reduction. There typically is less out then less in, as water is stored in the soil mix as well. So that's good. Abby's asked also, has Contech done any work on embodied carbon with your systems? I don't think embodied carbon's a big thing in the USA yet. Have you had a look at it?
No, not in a detailed enough way to have an answer. We have looking at it, if you want to think of it that way. That sounds more like an excuse than an answer, but it is not something that we've been asked often enough to actually go through the embodied carbon calculations for all the components.
I guess we can help you there too. Auckland Transport has asked Stormwater 360 to look at its embodied carbon and a lot of its devices. And Abby, basically, because the system is 10 to 20 times smaller than a traditional system, there is a lot less carbon, even in the concrete Filterra systems. But if you are really looking to reduce embodied carbon, the Bioscape system has much less embodied carbon than a large biofiltration system. Another question from Jackie Zoe of Auckland Council. Does the exposure to salt water in coastal areas affect the performance of the media or in the Filterra systems?
Yes, we just would avoid that. Oftentimes, if we're in a situation where we might have backwater in the system, we would suggest putting some sort of like tide flex valve on the system just to prevent that altogether. There's a lot of salts that just impact hardness and impact reactivity and uptake of other dissolved contaminants when you start adding salt water to the system. So we just don't recommend it.
Okay, so but being in a coastal area is okay, or is it just that backwater up into the media? You know?
Yeah, definitely okay. Yeah, it's just trying to avoid backwater situations.
Sure. And I guess that's the same with any sort of media filter. You know, the chemistry goes a bit haywire when there's salt water involved, doesn't it, really? Mm.
Yes, that's true. Although a
Sorry.
little bit of a twist on that is that we definitely have installations in cold climates where they salt the roads. And as long as it's not egregious amounts of salt, they can handle some salinity, you know, due to salts. And same thing with our media filters. We definitely have some monitoring, you know, coming from those colder climates where there are salts involved. But, you know, bottom line, let's treat the rain, not the ocean. Keep the salt water out.
Yeah. You've got some monitoring work up in Canada, isn't it, where they heavily salt the roads? Yeah.
Yes.
And in fact, they get blue swimmer crabs in freshwater environments. I've got another question here from Jacob Northridge. It's about the mulch. He said, would adding a layer of stones or pebbles on top of the mulch for aesthetic reasons negatively impact the system?
As long as the mulch is still there, I don't see, I mean, and as long as like it's not a hydraulic restriction layer, I see no issue with that. I mean, we put dissipation stones as part of the standard Filterra configuration to help with scour and that sort of thing. So, and dissipation. So, but putting it over the whole system, I don't think that would impact. I mean, you just have to think about like how much storage space you have in your system for trash and that sort of thing. That might start to impact that a little bit depending on how large your stone is and that sort of thing. So something to consider.
Yeah, I would not do that. I think what we're looking at in the illustration, I think in the background, that's kind of the most stone I'd want to see. I've seen a lot of systems that are stone through and through, like from side to side. So thinking about that from a couple of perspectives. One is that every bit of stone that you have sitting there is a bit of infiltrative capacity that you don't have anymore. So you've shrunk the area where water can go into the biofiltration bed. The other thing is when your sediment and inevitably leaves and trash and all that accumulate, what do you do then? You have to really remove the stones and then kind of clean out the gunk and junk that's, you know, accumulated between them. That's a very challenging process with stone as compared to mulch, which is just much easier to remove. So I prefer to keep the stone in the energy dissipation role, which you see just limited to the inlet where you can, you know, pick it up and clean it off and clean it out. And the mulch is still doing the bulk of the work from a filtration perspective and a pollutant removal perspective. It's a good question, though, especially in arid climates where they, you know, keeping plants alive or having mulch there is, they'd rather just, you know, zero escape the whole thing and forget about it. But, you know, you can't really forget about it.
Yeah, I can see the stones becoming a maintenance nightmare as you're trying to remove the mulch and having stones in there and the weight of them, and you don't want to wash every stone, do you? You know. Also, I understand that stones can also heat up quite a bit as well if you got, you know, which also, while they may prevent, you know, evaporation, they also heat up as well, which is not good for plant health. Okay, another question from Abby here. Microplastics, you guys done any monitoring on that? You know, I know PFAS is a big thing now coming in the USA. Yeah, have you done any monitoring on microplastics?
Sort of. We've done trash removal testing, and obviously you can't really get trash to move through it. So that's kind of macroplastics, which we usually think of in the 5 micron, or 5 millimeter or larger size range. On the microplastics side, a lot of times what people are really interested in is 6 ppdq, which is a tire wear breakdown particle that shows up as a major contributor or major component of microplastics. We have done some removal testing there, actually at that same Hillsboro, Oregon test site that we've tested the Filterra at for tape, and found good removals, in the 70–80% removal of the 6 ppdq in stormwater runoff. It was at pretty low concentrations. So we were able to get not quite down to the, say 4 nanograms per liter, kind of really, really low levels that are important for coho salmon in particular. But we do see good removal kind of on par with other biofilter type systems, conventional systems.
Thanks, Ray. Yeah, that is an interesting comment. There is microplastics. It's a broad category. If you're testing for 6 ppq, that's the nasty microplastic that's in car tires. It's killing all the salmon up in Washington area, up in the USA, and it also apparently can affect New Zealand's rainbow trout as well. So really good that you're seeing some good removal rates. Abby, I've also, last year's Stormwater conference, there was a paper on a traditional rain garden with microplastics showing they're really effective at a traditional rain garden. So I'm sure a Filterra would be also effective. And just kind of circling back on Andrea's question, has there been any comparison about hydraulic conductivity over time with conventional rain gardens? Do Andrea said, would a conventional, more traditional natural bioswale be better for high sediment sites? Have you done any comparison? Have you any comments on that question?
I've done just some kind of back of the envelope math on that, and it's kind of similar actually if you think about replacing the mulch entirely. So just to walk through that super quickly, if you figure a Filterra is going to be a 10th or a 20th of the size, say it's a 20th of the size of a conventional biofilter, you have a 20th of the area that you can accumulate solids on, right? So you have a much greater solids loading per area. That sounds like that's a problem. But if you think about the mulch's ability to kind of hold that, capture it, and then you replace the mulch, every 6 months or year, over the course of 20 years, which is probably about when we start looking at the useful life of both systems, you've had 20 to 40 maintenance intervals. With a biofilter that's a conventional system, you probably have not actually removed all the mulch at any time. Maybe you've just kind of topped it off as it needs to be replaced. A lot of the sediment and all that is in the system, like typically conventional systems, at least the maintenance protocols that I've seen, they don't include going in and scraping the systems. So over 20 years, you probably have about the same loading, on a per square foot basis. So that's super simplistic, but it's kind of how I start to wrap my head around the long-term performance, and certainly open to other, comments or ways of looking at that.
Yeah, we had a student once go around and test a whole bunch of existing rain gardens that we had the design data for, and I think 1 out of the 20 we tested was still working at design, and it was very vegetated. It was very vegetated, and it had quite a thorough kind of plant mass in it, so it was still had some permeability. And that kind of segues on good to the last question here from Teresa. What usually happens with the mulch? Does it go to landfill? What do you do to deal with it? Is it toxic?
Yeah, so it shouldn't be toxic. So I don't know how the rules there vary versus the rules here, but there are different classifications of waste, toxic versus special waste, and there are different kinds of landfills that accept different types of waste. So our classifications for toxic waste, it's not going to be normal stormwater that triggers it. Like if someone empties their RV septic tank, if it has a biological nature or something to it, then yes, that can definitely trigger toxic requirements. Or if there's a car accident and someone drops their antifreeze or motor oil or something, then definitely you can get in situations where that would be a hazardous waste. but most often it is just landfilled. You don't really want to put this back into the composting stream. Keep in mind that that compost will end up in conventional biofilters or people's gardens or whatever. And we see everything from, needles to, chemicals that you definitely don't want to be sending back through the kind of product chain or back out into the environment. So yes, it's unfortunate to take up landfill space with mulch, but think of it as not taking up your receiving water sediments, with those same pollutants. It's the best place for it.
And it'll break down in the landfill anyway, won't it? It pretty much disappear, turn to mulch, mush. Cool. Well, I think that's pretty much all the questions. Yeah, Jackie, I can flick you some more performance data on dissolved metals. That Jackie just had a question, where can he find performance data on dissolved metals? But most of the context studies do list the performance with copper and zinc anyway, with dissolved fraction, because Washington regulates dissolved metals, not just total metals. So that was just to finish that up. But thanks, guys. It was very informative and very useful, I think, for the New Zealand audience, just to see how much work has gone into Filterra over the years and what a great technology it's proving out to be over time. Thanks again. And if there's any more specific questions, we might send you an email and get you to respond to them. Thanks, guys.
Thank you.
Sounds great. Thank you, everyone.
Thanks, everyone.
See ya. Bye. So thanks a lot, everyone. Bye.